In this video, we're going to talk about how the idea of a conjugate generalizes in field theory. So just to set the stage, one thing you probably learned in high school is that if you have an expression like 1 over 2 minus the square root of 3, it's good manners for some reason. Nobody ever tells you the reason, but it's good manners to rewrite this expression in an equivalent form so that there are no square roots in the denominator. And one technique or strategy that they teach you for doing that is to multiply the numerator and denominator by the same thing. In this case, the conjugate of 2 minus the square root of 3, which is 2 plus the square root of 3. When you do that, you get 2 plus the square root of 3 over, and then this denominator is going to be 2 minus root 3, 2 plus root 3, and that works out to 2 plus root 3 over 2 times 2, that's 2 squared, minus root 3 squared. And then that makes that square root in the denominator go away. You have 2 plus root 3 over, I think that's just 4 minus 3, which is 1. So that all works out to 2 plus root 3. Okay, so this idea of using the conjugate seems to be a powerful strategy for getting rid of nasty stuff that you don't want in the denominator. But in high school algebra, the way that you usually learn the idea of conjugate is that taking the conjugate of something just means take the nasty part and flip the sign on it. So if you have a minus nasty part, then in the conjugate you should have plus the nasty part, and vice versa. And in abstract algebra, in particular in field theory, we're going to want an idea of conjugate that goes beyond this vague idea of the nasty part. So in this video, we're going to find out what that is. First, we need a definition. If f is a field, and E is an extension of F, an element A belonging to E is said to be algebraic over F, and that's all one term there, so let's underline the whole thing. Algebraic over F if there exists a polynomial P of x in f adjoin x, so a polynomial over f such that P of a is equal to 0. To put it in other words, A is algebraic over F if A is a root of some polynomial over F. So that's what it means to be algebraic over F. And this modifier here over F, absolutely necessary. So one thing that we're not going to prove here right now, but serves as a good example, is pi is not algebraic over Q. Another way of saying that is that pi is what we call transcendental over Q. And when people say that pi is a transcendental number, that's what they usually mean, is that it's not an algebraic number over the rationals. However, pi is algebraic over R, because there is a polynomial over R which has pi as a root. In particular, that one. Okay, so you can be algebraic over one field, but not algebraic over another one. All right, so that's our first definition. Now, here's another definition. Well, before we get into the formal definition, let's just talk about the idea of it. So let's say I have some algebraic element over a base field. Let's take f in this example to be the rationals. And let's say that our a is, I don't know, let's say 3 plus root 7. That's a nice number there. It doesn't belong to the rationals, but it does belong to an extension of the rationals. This belongs to, well, we could just say q adjoin the square root of 7, okay? And that may not be the only field extension containing 3 plus root 7. In fact, it most definitely is not, but it's perfectly good for this example. Now, here's a question. Is A algebraic over the rationals? So we're going to try and answer that question. Is A algebraic over the rationals? Well, one way that we can investigate that question is we can just say, okay, well, let's suppose we stipulate that x equals 3 plus root 7. All right, because we're going to try and come up with a polynomial in x over the rationals for which 3 plus root 7 is a root. Okay, so to do that, what I'm going to do is I'm going to say, well, if 3 plus root 7 were a root, that would mean I could substitute that for x, and the whole polynomial would have the value 0. So I'm going to kind of work backwards here. I'm going to say, well, what if x was equal to 3 plus root 7? Could I manufacture other relations from that that would give us a polynomial relation involving x in which 3 plus root 7 is a root? Okay, so one thing I could do here is I could just square both sides. That would give me another relation. But if I do that, I'm going to get 9 plus, let's see, that would be 6 root 7 plus, and then root 7 squared is 7, so I get 16 plus 6 root 7. And I'm no closer to having something nice here. So I could do that, and there's nothing wrong with that, but I'm not going to use that as my core strategy here. Instead, I'm going to go over here and move 3 to the other side first. X minus 3 equals root 7. And then square both sides. Squaring both sides gives me x squared minus 6x plus 9 equals 7. And then subtracting 7 from both sides gives me x squared minus 6x plus 2 equals 0. All right, so I believe that this is a polynomial. It's certainly over Q, and I believe it has 3 plus root 7 as a root. If you don't believe me, use the quadratic formula and verify that. So x squared minus 6x plus 2, that is an example of a polynomial that has 3 plus root 7 over as a root, and it is over Q. So the answer to my question about this being algebraic, 3 plus root 7, yes, it is algebraic over Q. But now the next question that you might ask is, okay, exactly what polynomials over Q have 3 plus root 7 as a root? So I'm going to write that down. Okay, question. Exactly what polynomials have 3 plus root 7 as a root? Well, first of all, let's suppose we call this polynomial over here x squared minus 6x plus 2. Let's call that f of x. Okay, so first answer is any multiple of that, any multiple of f of x certainly will have 3 plus root 7 as a root. Okay, but you might wonder if there are any other polynomials not included in that description that have 3 plus root 7 as a root. Well, okay, suppose there is some other polynomial. So suppose some other polynomial, let's call it p of x in Q adjoint x, also has this as a root. Well, okay, what happens then if I divide that p of x by f of x? What happens if we divide p of x by f of x? Then we get p of x equals f of x times some quotient, q of x, plus a remainder r of x, whose degree is less than that of f of x, so the degree is less than 2. But then, wait a minute, we said that p of a, that's equal to 0. A is 3 plus root 7. And then f of a times q of a also is 0 because a is a root of f. So then that leaves r of a. And well, if r of x has degree less than 2 and r of a is 0, and it has to be 0 because this is 0 and this is 0, so this also has to be 0, then that means a is a root of r. And I don't think that's going to happen for any constant polynomial. At least not if r of x is a non-zero constant. We are sort of assuming here that p of x isn't already a multiple of f of x. So this is going to be some non-zero remainder here. So a non-zero constant certainly won't allow for r of a to be 0. And a linear polynomial r of x won't allow for r of a to be 0 because, well, what linear polynomial over the rationals can you think of that has 3 plus root 7 as a root? I don't think you're going to find one. So we run into a contradiction here based on this, just evaluating this entire expression or equation, both sides of the equation at a. So actually it turns out that only the multiples of x squared minus 6x plus 2 have 3 plus root 7 as a root. All right, so what this means, so the key takeaway here is that f of x equals x squared minus 6x plus 2. This is the polynomial over Q of minimal degree and I'm going to add here the monic polynomial. Monic meaning, that's M-O-N-I-C. That means the lead term or the lead coefficient is equal to 1. So in other words, I have an x squared here rather than a 2x squared or a 3x squared, because I actually could come up with other quadratic polynomials that have a as a root. Just multiply all this by 2 or by 3. It'll have the same roots. So we're always going to pick on the one that's monic if we're looking for a single polynomial. All right, so it's the monic polynomial over Q of minimal degree having a as a root. And now that we've built up all this motivation, like 7 minutes worth of motivation, we're ready for our next definition. Our next definition is this. Definition. Let F be a field, and let E be an extension. And let A be an element of E. And we're actually not going to prohibit A from being an element of F itself. It's just this definition is going to be kind of boring if A is an element of F itself. So here's the definition. The minimal polynomial of A over F, the minimal polynomial of A over F, is the monic polynomial in F adjoint X of minimal degree having A as a root. Okay, now there are some things that we need to prove about this for this definition to make sense as written. So we need to show that, first of all, this polynomial is unique, because I did say in the definition it is the monic polynomial of minimal degree having A as a root. And also, well, okay, so we just need to show it's unique in order to prove that this definition makes sense. But we would also like to show, I'm just going to put over here, we would like to show that this polynomial is irreducible. That's going to be useful to know later. And one thing you'll notice up here is that that f of x, x squared minus 6x plus 2, that was irreducible. That's irreducible by Eisenstein for p equals 2. And so that's cool. All right, it's irreducible. And in our example, we actually showed that the only polynomials over Q having 3 plus root 7 as a root were the multiples of x squared minus 6x plus 2. So we'd like to show that the polynomials in f adjoint x with a as a root are exactly the ideal generated by the minimal polynomial, the principal ideal generated by the minimal polynomial. But all of these things here, we're going to show them later. We're not going to show them in this video. Okay, by the way, I know I say this all the time, but when I say over f, saying that is very meaningful here. It's very important, because if I choose a different base field, my assessment of what the minimal polynomial is going to change. So for example, let's go back to a equals 3 plus root 7 for just a moment. Okay, so the minimal polynomial for a over q, it's the one that we already found. It's f of x equals x squared minus 6x plus 2. We've already discovered that one. Okay, but the minimal polynomial for a over a different field, let's say over q adjoin root 7, well, that's going to be a different polynomial. That would be g of x equals, I think we can get a linear for this. It would be x minus 3 minus root 7. That polynomial exists over q adjoin root 7, so it's linear. And you're never going to do better than linear for a minimal polynomial because, well, non-zero constant polynomials don't have roots. So these are quite different situations here. Over Q, the minimal polynomial has degree 2. I'm going to mark that over here. And over Q adjoin root 7, our minimal polynomial has degree 1. And accordingly, we sometimes say that this element, 3 plus root 7, has degree 2 over the rationals, but has degree only 1 over Q adjoin root 7. Okay, one last definition. I promise I'm going to try and make this worthwhile. And that's back to the idea of conjugates. We talked about conjugates at the beginning of this video. Now let's close that loop. So let F be a field and E an extension of F. We say that alpha and beta, elements of E, these are conjugates over F, conjugates over F if alpha and beta have the same minimal polynomial over F. The same minimal polynomial over F. So, for example, going back to that polynomial we had over Q, f of x equals x squared minus 6x plus 2. That is irreducible. It is the minimal polynomial of a, or we'll call it alpha now. Alpha equals 3 plus root 7. Okay, but this polynomial has another root. Its roots are equal to x equals 6 plus or minus square root of 36 minus 4 times 2 is 8 all over 2. That works out to 6 plus or minus the square root of 28, that's 2 root 7 all over 2, which is 3 plus or minus root 7. And you can just as easily verify that 3 minus root 7 will not be a root of any linear polynomial over the rationals because, gosh, what would that look like? So the two roots of this polynomial, alpha equals 3 plus root 7 and beta equals 3 minus root 7, those are conjugates. But the funny thing is, this is a quadratic. There are two conjugates to see here. If I had an irreducible cubic over Q, then I would have a set of 3 conjugates, all 3 roots of that irreducible polynomial over Q. So what makes 3 plus root 7 and 3 minus root 7 conjugates of each other, it's not that one of them has a plus and one of them has a minus, although this is something that'll happen every time we have a quadratic over Q. What makes them conjugates is that they are roots of the same irreducible polynomial over Q, and therefore over Q they are indistinguishable from each other. As we showed earlier, this is irreducible, and these are roots. So one thing that we've proven is that there is always going to be an isomorphism of the splitting field of this polynomial over Q from the splitting field to itself that maps this root to this root, and vice versa. So these two elements, pure abstract algebra can't distinguish them, at least over Q. So anyway, that's a not so brief introduction to minimal polynomials and conjugates. And study this one really well because you're going to see these concepts quite a bit for the remainder of the course.